Hello and welcome to the Data Engineering Podcast, the show about modern data management. Introducing RudderStack Profiles. RudderStack Profiles takes the SAS guesswork and SQL gruntwork out of building complete customer profiles so you can quickly ship actionable, enriched data to every downstream team. You specify the customer traits, then Profiles runs the joins and computations for you to create complete customer profiles. Get all of the details and try the new product today at dataengineeringpodcast.com/RudderStack. You shouldn't have to throw away the database to build with fast-changing data. You should be able to keep the familiarity of SQL and the proven architecture of cloud warehouses, but swap the decades-old batch computation model for an efficient incremental engine to get complex queries that are always up to date. With Materialize, you can. It's the only true SQL streaming database built from the ground up to meet the needs of modern data products. Whether it's real-time dashboarding and analytics, personalization and segmentation, or automation and alerting, Materialize gives you the ability to work with fresh, correct, and scalable results, all on a familiar SQL interface. Go to dataengineeringpodcast.com/materialize today to get 2 weeks free. Your host is Tobias Macey, and today I'm interviewing Brian Platz about using JSON-LD for building linked data products. So Brian, can you start by introducing yourself?
Yeah, thanks, Tobias. Happy to be here. Brian Platz, as you said, I am the CEO and co-founder of Flurry. I've been building enterprise software my whole career. Flurry, really, for the past 4-ish years. It's an open source graph database product. And happy to talk to you about JSON-LD, and which has a strong intersection with what we do.
Absolutely. And do you remember how you first got started working in data?
I have been building software companies really my whole career. So I'm on, I think, number 7 at this point. And as those companies mature, you end up typically acquiring adjacent products and trying to integrate them. And that's really where, data always ended up becoming the obstacle for me. There's the marketing message of having a product suite. And of course, the idea of integrating apps and thinking about, challenges like UI and experience and seamlessness across various applications. That always seems like it'll be a challenge, but the challenge is always in the data, and mostly because the data doesn't speak the same language. So that's what's really led me down the path of becoming very focused on trying to solve that problem.
And in terms of the conversation today, I mentioned the idea of a linked data product, and I'm wondering if we can just start by unpacking that term and what it means and some examples of when you might want to build a linked data product.
Yeah, so I think everyone's probably heard the buzz around data products by now, so we don't have to spend too much time on that part of it. I'm excited about data products because I have been seeing and think an inevitable transition happens here, hopefully in the shorter term than longer term, where instead of people going out and just buying apps where data is an artifact of an app, we actually flip that completely around, where people focus on data first and foremost, and apps can kind of come and go, but you're managing a very high integrity, trusted set of data in the middle that doesn't have to change. And I think, of course, machine learning and AI has been a big driver for that happening. And the fact that we now have data products, I think, is a great example of that. The linked part of this, linked data product, linked data really implies, I think, to most people who are in the space, kind of 2 things. One, it implies graph, as opposed to relational or rectangular kind of shaped data. We're definitely focusing on graph data here. And then what it invokes for most people as well is a set of standards put out by the World Wide Web Consortium around linked data, really in an effort to create kind of a similar environment that we have for the web, which uses HTTP kind of fundamentally, instead creating a decentralized data network. And what are the standards that goes by? And machines would be the primary consumer of that. There's kind of a third part that the linked data adds in, at least from my perspective and where we have to go with it, and that is various forms of cryptography that enable the data to be verifiable, trusted, very sophisticated permissions embedded within the data. We call this data defending itself. So I think for this to really reach its potential, we have to bring the cryptographic sort of conversation into linked data. But yeah, those are kind of what we mean by adding that one word in front of data product.
And another term that folks might have come across or understand that is at least related to this concept of linked data is the idea of a knowledge graph. And I'm curious if you can explain some of the overlap between those ideas of a knowledge graph and a linked data product, and in particular, explain where they might be divergent from each other.
Yeah, I think of them. I don't know that there's a formal dictionary definition of these, but I think of them as roughly synonymous. So, a knowledge graph is a graph database made up of linked data based on these standards. So, this is a knowledge graph from my perspective. I'm sure there's some other people with different definitions. But yeah, knowledge graphs really form around the concepts, the foundational concept of RDF, which is a W3C standard. And then there's all kinds of things that build up on top of RDF. And I'm sure we'll probably end up talking about that a little bit more. But when we talk about JSON-LD in particular, I'm excited about it because it does actually use RDF under the hood, but a lot of people don't know that or don't even have to know that. They're just working with JSON. And so I think it ends up making things much more approachable for folks who know JSON but might not be as familiar with concepts or like RDF or even graph. It's a nice entry point into it. So that's what excites me in particular about JSON-LD as it relates to this.
And now digging into JSON-LD for people who haven't come across it before, the LD suffix, it stands for linked data. And I'm wondering if you can talk through some of the applications of JSON-LD in this space of RDF, the semantic web, which is where RDF largely found its roots, and some of the domains in which JSON-LD is typically used.
Yeah, so where we see JSON-LD or even RDF in general is where there needs to be interoperability across data. And this really implies a decentralized context. So that, people who don't necessarily have to know or have an agreement about a schema or vocabulary up front are able to actually merge, combine, and link data together. And it's because it handles these sorts of standards. So the interoperability across domains is the key here. And of course, I think as most data scientists know, they spend a huge amount of time on their data just trying to get it into a common format. So imagine that work's already done, right? It's already in a format that a machine can automatically figure out what it needs. And of course, that's going to speak to the interoperability of data challenges. Now, those exist certainly across boundaries like organizational, governmental boundaries, but those also exist inside of companies, in a financial services company, finance and risk probably calls things which are identical to sales and marketing in the same organization by different vocabulary terms, even though it's the same underlying data. So this exists not only across these boundaries, but even inside of organizations. The JSON serialization, I think, brings familiarity for folks. So I don't think you could find a developer who hasn't worked with JSON at some point. So people are familiar with that concept. And in fact, a simple JSON document can itself just be used as JSON-LD. Now, it doesn't bring all the special characteristics into it unless you sprinkle it with a few extra things. But you can literally just take a JSON document, transact it, and use it almost like a document database, but you have full graph indexing and query capability. So where we see it, the specific domains where probably the most adoption has happened has been the push of Google and Microsoft to use this across embedding this inside of web pages. And now almost 50% of the web has JSON-LD in it. So this is, JSON data embedded within the actual web page, and it's used, for no surprise, by machines to figure out what a web page is talking about, et cetera. And in fact, my guess is most people in your audience end up using JSON-LD tens, if not hundreds of times a day without ever knowing it. If you've posted a tweet, if they're still called tweets, I don't know what they're called anymore, but or shared something on LinkedIn and, a nice description, an image of that web page you shared comes up, that is because there's JSON-LD embedded in the web page that the machine is running, and we have interoperability there across services without the web page provider and LinkedIn or Twitter or anyone else having to collaborate on that ahead of time. We're seeing it more in regulation, and we're seeing it more in an area that I would call intelligent agents, which is really AI being able to go out and find and not only discover data and information, but because of the semantics and the linked nature of it, be able to automatically figure out what that data means. So it's significantly more valuable for AI or other agents to be able to understand information.
And going back to your mention of the usage in Google and a lot of these social media companies of that linked data, it's, if I'm not mistaken, you're talking about the Open Graph specification, where if you inspect the header of a web page, you'll see an OG colon prefix to identify what attribute of that Open Graph you're specifying in the page metadata.
Yeah, Open Graph and increasingly schema.org, which is actually the schema that schema, if you will, vocabulary I'd probably refer to it as, that Google and Microsoft put out. So web pages are described sometimes in both, sometimes in one or the other. And one of the nice things, which we'll probably get to about this space, is that it doesn't live in a world where you think that the whole universe will agree on the same schema or terminology. So there become ways to map schemas together and say this thing over here means the same thing as this thing over here, where you don't have agreement on those. We might get into that a little bit more. But yeah, definitely Open Graph, schema.org are heavily used and recognized by the major search engines and other services that are leveraging web pages.
And so, for application developers and data practitioners who are thinking along these lines of JSON-LD or linked data, in the overall data lifecycle, there are usually a few different stages of the creation and processing of information, where an application is generally responsible for the either capture or creation of that data, and then there are data pipelines and then data analytics that will extract and make use of that information. And so I'd like to maybe talk about some of the ways that JSON-LD and these linked data concepts are present in those different stages of the life cycle. So maybe talking first about the application development and some of the concepts of domain modeling within the application, ways that JSON-LD and these schema semantics come into play in that development process.
Yeah, so there's quite a bit there in that question. And I think a good place to start is RDF itself. And one of the nice things, so to answer the question, where is this used or how do you think about it? What is RDF? RDFs are triples. It's technically goes by subject, predicate, object, the three elements of it. But if you map this to like an Excel spreadsheet, the subject is really like your row number, the predicate is really like your column, and the third part of it is really like the value in that cell. So it's an extraordinarily simple way of representing data. In fact, any piece of conceivable data can be represented as RDF, which makes it a phenomenal way of just storing any information because it's simple, it can store anything, there's zero limitations. So the questions come up on how do you serialize it and what are the best practices for it. And so I'll mention a couple things there and we'll kind of build up to the final part of your question. So in JSON, when you think about RDF or triples, what you're really doing is the second part's the predicate, which is really the property, and the value are just your key value pairs in a JSON object. It's as simple as that. It's first name Brian in the case of me. But how do you uniquely identify a row? And there's a special term in JSON-LD where the key is @ID. So @ID is where you can give something a global identifier. Now, it doesn't have to be global, it can be relative, but in being global, it means that it's more easy to combine with other data that's using the same global identifiers for things. Again, you can sort of map things together after the fact. So you could say this global ID that someone was using over here is the same as this other global ID that I was using over here. And the systems that manage knowledge graph data will be able to automatically infer that. So when you query for either one, the same result will come out. So kind of this magic happens in the background. So when you create JSON-LD, what you're really trying to do is use for your keys that you're doing, like first name, instead of just calling it first name, ideally you're using some sort of standard vocabulary. Again, you don't have to because you can always address it after the fact. But we already talked about schema.org. Schema.org has a very robust way of representing people and companies and other things. And in fact, it saves you a lot of time as a developer because there's a lot of nuances when you model out data that a lot of smart people have already modeled out those concepts for you and thought about the edge cases that normally you think about or run into in version 2 of your app or version 3 of your app. But there's nothing stopping you sort of doing the traditional app. If you're developing a new app, application development, I'm just going to kind of create my data however I want. That's still a fine thing to do. You just want to be able to leverage these common ontologies. And I think that is probably enough for that question, but we can certainly build on it from there.
Absolutely. And now moving into the stage of I have this data that exists in an application or in some source system that I want to consume and perform analysis on for data engineers who are working on that process. I'm curious if you can talk to some of the ways that having the RDF specification or the JSON-LD representation already present in the application simplifies their work of doing that extraction, in particular, maintaining the context of the information that they're trying to extract. And for cases where there isn't already that representation and it's just a tabular structure like you will rip out of any database or just a JSON API without these linkages embedded in it, some of the ways that the engineers might think about appending the additional contextual data in that JSON-LD format to simplify downstream operations.
Yeah, so one of the big benefits that you get is that if I have two JSON-LD files, say, or databases, however I have that data, if one file, is for customers and another file is or database is for orders, those can exist independently, but they can actually be queried as though they're the identical database. So you think about all the effort and work that we put in today to extract our data out and put it into something like a big data warehouse, really with the aim so that we can run queries across it. We're probably doing additional transformations, in that process to normalize schemas or other things. There's a lot of work involved. And if the data natively sits in this format, all that work goes away. In fact, you don't even have to have the data physically co-resident with each other to query across it as though it's one database. So there's these great advantages to doing that. One thing that is also great about Graph is it's really a superset of almost every other type of way of managing data. Especially with JSON-LD, it retains a lot of the simplicity of a document database like MongoDB or something like that. It's incredibly powerful from an analytics standpoint, which is usually why people go to relational databases because they're going to be writing complex queries and be doing analytics on that. This data not only does all of those types of analytics, there's a whole additional set of analytics that become easier once your data is in a graph. And because it's a superset of really these other capabilities, it means that you can flatten it as well. So even if I have JSON-LD data as this native, really rich, it's the most rich way I believe you can even represent information. If I want to flatten that data into rectangles so I can stick it in a SQL database or put it in a CSV file, I can flatten relational. You can't go the other way. You can't take relational data and without a lot of transformation work, try to turn it into a graph, but a graph can be easily flattened. So it creates immense flexibility. It creates a lot of reusability aspects of the data. And the challenge is that our data usually doesn't originate like this because almost all apps are using relational databases now or some form of that. So the shift that I believe we'll see, that I think we've started to see and will continue to see, is that instead of favoring relational databases as the system of record, we start using Graph as the system of record. Traditionally, Graph has been used more for analytics. It's more after the fact. Some system of record is maintaining the data, and then ultimately I have some transformations where I'm putting it into a knowledge graph or doing other things so I can do more sophisticated analytics with it. But if we can just sort of move that up where the graph is the operational data store, then I think it not eliminates, that's a strong word, but substantially reduces all of the data engineering work that has to go into making it usable for data scientists or machines downstream.
This episode is brought to you by Hex. If you're a data person, you probably have to jump between different tools to run queries, build visualizations, write Python, and send around a lot of spreadsheets and CSV files. Hex brings everything together. Its powerful notebook UI lets you analyze data in SQL, Python, or no code in any combination and work together with live multiplayer and version control. And now, Hex's magical AI tools can generate queries and code, create visualizations, and even kickstart a whole analysis for you, all from natural language prompts. It's like having an analytics copilot built right into where you're already doing your work. Then, when you're ready to share, you can use Hex's drag-and-drop app builder to configure beautiful reports or dashboards that anyone can use. Join the hundreds of data teams like Notion, AllTrails, Loom, Mixpanel, and Algolia using Hex every day to make their work more impactful. Sign up today at dataengineeringpodcast.com/hex to get a 30-day free trial of the Hex team plan. Digging more into this concept of the graph representation of the data, I'm also interested in your perspective as to how necessary it is for that to be stored in a graph native database versus using this flattened representation that you were mentioning, or using something like an adjacency list in a relational store for being able to represent that graph structure.
Yeah, I think that is it necessary? No. I mean, we've been combining data sets and merging data sets together for a long time. I would make the argument that it's not scalable, right? So usually it's a specific problem that we have to solve, that we go about getting the data, we create our pipelines, we create transformations, we do whatever we need to do to focus on building out that data. And we're done. I mean, we'll accomplish the task. But today we have a pretty limited set of data that we're doing this work with. And part of the reason, there's a lot of reasons, but the one I'll focus on here is that process is expensive and it's not super scalable, which limits how much data you're able to do this work with. If it were all more natively in this format and machines can automatically infer what the data means, can automatically follow links and merge data together, then it makes all that work we have to do to getting to that end state unnecessary, which means we have a more scalable process. I believe it's estimated that about 96% of the data that corporations end up producing from their applications, et cetera, is dark, meaning that it's never used. And in some cases we're paying to store it, but we'll never use it. This is a way of actually making data more natively, much more usable, much more scalable, and be able to not only leverage it inside of our organization, but think about the challenges and the work we do just to, get our CRM data with our ERP data combined into a single thing that we're running queries against. Now think about taking parts of that ERP data and sharing it to other partners and external organizations. A whole nother layer of that work has to start again, whereas this format eliminates all of those components. It just makes sense to do this, but of course, it's not what we're used to doing, and I think that's one of our biggest challenges right now.
Another aspect of what you were just describing with these linked data representations and being able to easily translate between the vocabularies used in your example between the finance department and the sales department is another conversation that's been happening in the data space recently around this idea of the metrics layer or the semantic layer for the data that has traditionally been encapsulated by the business intelligence layer, but is now being moved into a separate concern so that you can use it in more than just the business intelligence context. And I'm curious how you see these concepts of the metric store versus data linkages and shared vocabularies as either corollaries to or competitors for the same intent.
Yeah, it's a really good question. And I'll actually focus on the word you used, which is layers. And it's a layer. And so this type of data natively embeds semantics in it. And the semantics are highly reusable and can actually be described by other vocabularies that allow mappings between semantics. To accomplish this with traditional data, or most data that we have today, we have to add a layer. Just like we have to add a layer like a data warehouse to query across data sets, just like we have to add a layer for, how do we protect data after we move it into the data warehouse and assign permission. Our focus, and this is a little bit unique in Flurry, is we allow that data to be what we call programmable, but we can embed security directly into the data tier, which allows anything that needs access to that data to be able to query for it, but they're only going to get a subset of the data that they natively have in it. So using a traditional sort of siloed data relational database that's coming off the back end of an application, all these things you're talking about, adding semantics, adding all of these things can be done, but we're adding layer and layer and layer and layer to accomplish them. This is a way that we can structure data fundamentally that those layers become unnecessary.
Particularly speaking in the world where most people are right now, of they have a data warehouse, they have their data pipelines for extracting from source systems, combining it into a shared query layer. There's that word layer again. I'm wondering if you can talk to some of the data modeling exercises that are necessary to start embedding the contextual awareness into the data versus it being an after the fact exercise that has to be done, or an exercise that has to be part of that extract process, and instead making it native to the data itself rather than being something that is imposed upon it ex post facto.
Yeah, and I'll focus on how you do this in JSON-LD just to give a concrete representation, because there are alternatives of doing this for other types of data in different serializations. But in JSON-LD, I already talked about one special keyword, add ID, and this can give a global identifier for an item that can allow things to be mapped together. And again, you can sort of map different add IDs that you find out later really talk about the same thing. Another very common one you're going to see is at type. And this is where you're assigning the data a class. And this type of data natively supports super and subclasses. So it's also a way of kind of combining data, but it's also a way of adding powerful capability to it. I'll use schema.org since we talked about it as a simple example, but there's a lot of very industry-focused ontologies like IDMP around, pharmaceutical products. There's FIBO around financial, and the list goes on and on. But in schema.org, you have things like movies, books, and they're both subclasses of creative works. And in a JSON-LD database, even though I said this is a book or this is a movie, I can basically do select star from creative work, and all the books and all the movies will come out because it understands a notion of class hierarchy within your data. So it adds very powerful capabilities. You can actually do the same thing with properties. You might have a field called mother and a field called father, and they're both subproperties of a field called parent. And just natively, you can say select, parents for Tobias, and it'll return both mother and father for that, for example. So those are two kind of common special keys you'll see in JSON-LD. You do not have to use those. So I want to be clear with that. Just a plain old JSON object will be able to, in most systems, transact, but those add value to it. How do you do the mapping, specifically, was your question. And I wanted to lead to the third kind of common special key that you'll see in a JSON-LD file, which is at context. So the at symbol in context. And what at context does is it allows you to map the names of the keys that you're using to a global identifier. And so it doesn't really matter in your data, in your JSON, what key you use for first name, given name, F name, G name, just name. You can call it whatever you want. You can use this at context to say anywhere you see a G name for given name, it actually is, what I mean by this is, I'll use schema.org again, schema.org /G name. So you're attaching a global namespace, in this case schema.org, to that field. And now anyone receiving that, when they see G name in your file, and the machines automatically infer this, by the way, and kind of expand it out. But even as a human, as soon as you see G name, you know that that is actually referring to this vocabulary that is published and open, that's very well vetted, and you have an exact meaning of what that is. You also can learn other things, like a given name always exists on a person. So now I automatically know this data is a person. And in a database, a knowledge graph database, you could say select star from person. All of a sudden, all the people show up. Even though you never said that data was from a person, the fact that we said it has a G name, and G name stands for a given name, and a given name's always on a person, we're able to infer automatically additional data. So a lot of things we're writing custom Python scripts or other things to infer can just natively be inferred in this data. But your question was, how do we create ththese mappings? So in JSON-LD, you use the at context field, and there can be some additional layers on top of that, but that's a very simple way of mapping your raw JSON data into something far more useful in a global vocabulary.
Digging into that hierarchical aspect of the data and being able to build these inferences brings to mind the question of performance and some of the ways to address the lookup cost of all of these different attributes, particularly given the fact that, to your point of, I want to find all of the people, but all I have is the G name to indicate that this is a person, which brings to mind the idea of sparse matrices and some of the performance challenges around sparsity in data sets. And also to your point of making sure that this G name is a context that I apply to these different records or to this specific field. In the world where most people are operating, that is typically done through the transformation of the data from the raw layer. So using ELT approaches as an example, you load the raw data. Now I'm going to coalesce all of these different column names into a single column name to ensure that I'm calling this one field the same thing everywhere in downstream use cases. In this linked data approach, instead, I don't care what the column name is. I'm going to apply this contextual attribute to this column instead, and then I don't have to do those transformations. And so it's an emergent schema rather than an enforced schema. And so I'm interested in talking through some of the ways that these emergent properties of the data will impact the performance characteristics of the system and some of the architectural approaches to mitigate that concern.
Yeah, well, I'm glad you asked specifically about architectural approaches, because I think that is the primary mechanism, at least that we think about, to mitigate these. But yeah, if you are, so there's a number of very simple ways that kind of layer on these standards to do things like subclassing. That's a pretty simple thing. Doesn't have huge performance implications. There's additional standards that allow you to develop these immensely rich ontologies. And one of the most commonly used ones for those that get to that far is OWL. And I'll say about these standards, the neat thing is that all of this is just represented as RDF data. So, you think about something like a standard schema in a relational database, and of course you set up your schema up front and you have a special command for establishing your schema. Think of your schema itself just being described as data. But it's not just schema, it's so much more beyond that. So OWL can actually express concepts that are NP hard problems, meaning that there's, computationally, certainly quantum computers might make a big impact in this, that it is going to be immensely difficult for a computer to figure it out. So one of the things they do with OWL is they break it up into several subcategories. Kind of an easy category that computers can figure out really quick, sort of a more sophisticated one, one where it can be figured out entirely with, for example, forward chaining rules, and then all the way up into, these concepts that really aren't computationally scalable, I guess is what I would say. So one thing is if you are getting into this area where you're using these sophisticated rules applied to this data, and by the way, one of the reasons to use this over like custom Python is that it's completely reusable. Once you develop these rules, not only are they data themselves, you can query for the rules, you can sort of update them and do these things, but you can just layer these rules on top of any data that talks about this. And all this inferencing and magic kind of will just automatically happen for it. In any compliant system, it'll all just work in. But you have to sort of work within the set if you're going to try and run these in real time, for example. Or maybe I don't need to run them in real time. There's you'll see examples, for example, in financial services, where it'll have a bunch of things in the ontology that says, okay, if a person has at least 2 of these 5 types of accounts, and the combined balance of all the accounts exceeds $1 million, and the account is open, and this and that, that's an ontology rule that can be expressed. Then they're going to be a high value customer, and you can select star high value customers, and all of a sudden your high value customers show up. But that's a bunch of computation that would normally happen in a Python script or something like that. And if you have immense volume of data and this is changing all the time and you're trying to run it in real time, it's a consideration to have. Do I need to run it in real time? Can I run it on the side once a day? Is that good enough? Do I have too much volume that if I run it in real time, it's computationally intensive? And do I scale that back? So you have to decide what you use and don't use, and it depends on your use case. As far as how can we address it with architecture, the thing that we're super excited about is that we have broken up the database into two pieces. So traditionally, a database is a server you put up, and it handles all your updates and it handles all your queries in one server. We can't think of a good reason, except for just a legacy, why that is. We can actually split these two functions completely, which means our query servers become ephemeral. Our database servers, we can spin them up, spin them down. We can put them in all of our data centers right next to our apps if we want. They cache segments of the data that are hot in memory that keep updated all the time, and allows you to push the compute layer to the edge and allows you to have horizontal scalability of that. So even if you want to do some of these computationally intense algorithms, what you can do is actually push them to your consumers, push them away to the edge, and you don't have to maintain these big centralized servers that are trying to service unknown load for a whole bunch of users. So there are architectural ways of making this better as well.
For people who have already invested the work of building up these centralized stores of their data, usually in something like a data warehouse or even a data lake or data lake house, whatever you want to call the thing that you have all of your data stuffed into, they've already done a lot of work of trying to normalize the schemas and bring together all of these records into a common representation, often through a lot of brute force and hard work. What are some of the lessons that they should be thinking about as far as their overall workflow to be able to bring in some of this contextual knowledge of their data, embed that into their workflows, and being able to start layering on these capabilities of the emergent properties of these kind of schema linkages without necessarily having to do a complete rewrite or re-architecture of their system, and instead being able to add these data linkages and these ontologies into their workflow so that maybe eventually they move to a new architecture, but they're able to actually start taking advantage of these concepts today.
I'll talk about what I think is the most logical and easiest way to get into this in the scenario you pointed out. We're seeing more and more that there's actually drivers that force you into this scenario. So one is regulation. FDA is looking to speed up vaccine development, and they're looking to push the pharmaceutical companies to be able to submit data using RDF, using JSON-LD, because it's decentralized and interoperable. It's part of that process. Department of Homeland Security in the US is looking to use verifiable credentials, which is just a cryptographic wrapping around JSON-LD data to facilitate customs processing. So they can show a chain of all the goods that went into a product and make sure there aren't, tariffs in there. In order to ship data across boundaries, if you have to represent it as linked data, then of course you're forced to do this. It sort of doesn't matter the work you did with other things. The regulators are telling you to do this. We're seeing people wanting to leverage AI as being another driver. If you really want the AI to be able to understand what the data means natively without having to tell it everything and want to scale more of your data for consumption, that's another big driver. But if you don't have one of those drivers where you don't have a choice as far as representing your data like that, we've talked about some of the benefits that you would get out of having that, but kind of where do you start? And the most logical place that people start with this data and the concept of knowledge graphs is they create a knowledge graph which has the class hierarchies and everything that represents their domain, their business. And they map their existing data that they have into that domain. The idea there is that you can introduce other business users to be able to find data. It effectively accomplishes kind of schema on read. So if you have different parties you talked about semantics and mapping that, that's a way to automatically map that. A pattern we're seeing is to build that out, catalog your data, and then have new data sets registered in that, and have machine learning or other services automatically kicked off if they have permission to see it, and enrich this catalog with additional metadata to improve the findability. So that's a real logical place to start. And once you have this kind of domain described and this knowledge graph described, you can start to, instead of just pointing to all these different data sets and enabling some of this metadata and facilitation, you can actually start to represent some of that data natively in a knowledge graph format over time, and it sort of just plugs in to the nodes of your overall graph. So that's where we're seeing most people start. When they don't have one of these external pressures that's forcing them to do something.
And as you were talking about the idea of cataloging, it also brings up the question of data catalogs, data discoverability, which is another piece that is a separate layer, going back to our earlier conversation, and another set of exercises that is necessary, usually bringing in something like a business glossary or bringing in different people to add documentation on different aspects of the data through wikis, labeling, lineage. I'm curious how this idea of the linked data attributes as the embedded context of these records and the schema layering and layering on these ontologies factors into that question of data cataloging and discovery, and maybe some of the ways that it will at least accelerate, if not obviate, the need for these explicit data documentation exercises.
Yeah, I think about, well, those who have used data catalogs understand the value that they potentially bring, although I know, some implementations are more successful than others. So what I'm referring to when I talk about this knowledge graph acting as a data catalog is sort of like data catalog 2.0. So similar ideas, similar benefits, but how do we bring even more capability into that? We focus on this idea of first modeling out your business, which is an enhanced or sort of a knowledge graph version of a data catalog, and then being able to use that structure you set up, not just for humans to find out, what data sets have store sales information, but to actually allow machines to natively do that and bring some of this more sophisticated query capability to those particular assets. Once you have that hierarchy established, you can also start using it for automatic classification. So if you're using, natural language processing on unstructured data, you're sort of running it through a generic model, but your business isn't generic. Your business looks for certain things in that. This hierarchy is a native way of actually classifying information and giving a lens to machines, machine learning, or other algorithms to do that. At Flurry, we extend this to be able to handle permissions and permissions in a hierarchical way. Once I have this kind of set up, I can tag nodes, I can establish certain rules, and it's going to apply to all data assets that sort of flow down from that. So you just start unlocking a lot of capability to taking this concept of this catalog into more of a concept of an ontology. Solves the same thing the catalog did, but really starts to bring in all of this additional capability as well.
Another thing that comes to mind as we're talking about layering on these ontologies and the schema and the embedding of this contextual information into the document that has the attributes is the idea of schema enforcement or attribute enforcement. I'm thinking in terms of things like the schema store in things like Kafka, where you can say, this is the schema for this topic, so any event that comes in has to conform to this structural specification of the data. I'm curious some of the ways that enforcement of attributes and data types can come into play with these contextual elements that are being appended to the documents themselves, and that idea of type and structural enforcement.
So I think most people who've worked with relational data are used to, traditional SQL like schema enforcement. And there's a couple nuances, but as it relates to the closest analogy, the thing that we use in our product and other knowledge graph products or graph products use is the standard called SHACL, which stands for Shapes Constraint Language. And it allows you to establish very, very sophisticated rules as far as what data is allowed or not. And you can really use this in two ways. One is you can use it as a reporting engine. The actual reports or the data quality scoring that come out the other side comes out, again, just like everything in this space, as data. So you can easily ingest that into an app, parse it, you can query for it, whatnot. But if you're acting as an operational data store as well, it can do enforcement like traditional schema on a relational database would. It'll reject something if it's not a string. Of course, you can do kind of the next level up where you're doing cardinality min and max, you're doing regular expressions, but you can take that to entirely new levels where you can actually peer through the graph and say, this is a valid value if it's connected to this type of entity, and that entity has a value greater than X. So you can really start linking it through the graph and have validation happen in ways that you just cannot even approach in traditional schema enforcement in SQL. The twist that I mentioned is that the whole purpose of this is to end up having fully composable data. You can just layer data sets together. It's like it was in a data warehouse. It doesn't even need to be in a data warehouse. You can issue queries across multiple data sets dynamically. Well, when you do that and you're combining data together, you can't enforce things like cardinality constraints. For example, if I had Tobias in my database and you had it in your database, and in one it said your eyes were brown and the other it said your eyes were blue, even though that would be eye color would be single cardinality, I now have two different values for the same property. So in each of those data sets, I can enforce single cardinality, but when I merge them together, I can't necessarily choose a winner. All of a sudden, everything becomes multi-cardinality. And this has benefits and challenges, but it becomes a slightly different way of thinking about composable data. It's a challenge that you just simply cannot get around. And this is where you might apply something like a shackle rule after the fact, where after I merge these data sets together, I want to see if it still complies with my schema. The nice thing about shackle, again, it's just data. It's like another data set. It's incredibly reusable. You don't have to recreate it. You can associate it with things and use it in so many different ways. But that would be an example of how you approach schema and how some of this kind of composability does change things beyond what people are used to thinking about.
This episode is brought to you by Datafold, a testing automation platform for data engineers that finds data quality issues before the code and data are deployed to production. Datafold leverages data diffing to compare production and development environments and column-level lineage to show you the exact impact of every code change on data, metrics, and BI tools, keeping your team productive and stakeholders happy. Datafold integrates with dbt, the modern data stack, and seamlessly plugs in your data CI for team-wide and automated testing. If you are migrating to a modern data stack, Datafold can also help you automate data and code validation to speed up the migration. Learn more about Datafold by visiting dataengineeringpodcast.com/Datafold today. And in your experience of working in this space of linked data using JSON-LD as the representation for being able to embed all of this ontological and contextual information, what are the most interesting or innovative or unexpected ways that you've seen those concepts applied to data workflows?
I'm really excited, I think, about new things that this opens up that would, I think, be extraordinarily challenging with today's technology. And we've been doing a lot of work in verifiable credentials. And this idea, I've talked about embedding permissions and security and trust into the data layer. Right now, this always sits in the app layer. And when we suck our data out and we copy it and we paste it into the data warehouse, we lose all the data security rules. We have to try and recreate them or limit access or whatever. So, embedding security into the data is a very, very powerful concept, but now we can start even extending that further. And if we think about this data ultimately forming the World Wide Web of data, if you will, where these data sets can interconnect, be composed, etc., one of the coolest concepts is to be able to cryptographically have ownership embedded around the data and allow people to pluck nodes out of the graph, if you will, and store them in a wallet on their phone to prove things about them, have complete control over their data and their data ownership, so not have to relinquish that data. We are doing a ton of exciting work around this right now with skills and credentials in higher education. Flurry's powering a big network of a lot of the big names in higher ed to be able to have reusable credentials. When you apply for a job, you can prove you have degrees. There's no way of faking any of this information. You can prove it was issued by MIT or by Arizona State University, all independently with zero third parties. So this concept of decentralization and trust with zero third party involved is super powerful. It creates sovereignty over people owning their own data. Think about your financial records. Think about, proving that you have a job without to the mortgage company without them having to call your employer. Think about being specific when you go from one doctor to another, pulling your medical records into your wallet and be able to very specifically share with a new provider which parts of that record they get. They can independently verify them without having to, even though you're the one that gave it to them. So this idea of giving control over data, and then we start to wrap a special field of cryptography around zero knowledge cryptography around it. And it starts to open up being able to do analytics across data where you never physically share a single piece of data. So there's a lot of exciting types of cryptography that can wrap around these concepts that can enable data analytics across, competitors without them ever sharing a single row or record of data. They can still do things across boundaries. So a lot of exciting opportunity once we solve some of these fundamental rules and problems and store data in this really, really rich native way.
And in your work of building Flurry and working in this space of linked data products and exploring the capabilities and the challenges, what are the most interesting or unexpected or challenging lessons that you've learned in the process?
One of the challenges I think that we have faced the most is that we live in a world where we've grown up thinking about data in a rectangular way, whether it's using Excel, which is rectangulars, relational databases, more rectangles, everything's rectangles. And, the shift to starting to view data as a graph and kind of through this connected cloud, it's a big shift, and it's a hard one sort of to go through for some people. You need to pick up the concepts, I think, gradually. And one of the things is, well, all these ideas sound great, and it sounds like it solves the world's problems. It's still just not the way the world works. So it's not practical to jump completely in. You have to kind of come in gradually into it. JSON-LD excites me a lot because it brings, it's relatively new serialization of these concepts that have been around for a while. But of course, as I started out saying, everyone knows JSON. So it just brings instant familiarity for anyone who's worked with data in a JSON format, which is everyone, to some of these ideas. And it provides a foundation that you can just start building, a familiar foundation. You can start building some of the additional concepts on top of very gradually. And so I think that's kind of what we need. And one of the reasons we're so excited about JSON-LD in particular is that we think it's going to open up these concepts to more people and increase adoption more rapidly.
And for people who are listening to this conversation, they're excited about the ideas of embedding context, having these automatic linkages between different records and ideas. What are the cases where either the linked data approach in general or JSON-LD in particular are the wrong choice?
Linked data in general, I mean, if data is never going to be needed to be reused or interoperable, part of the whole point of this is to make data more interoperable. So, if you're throwing something up and that data is never going to be used downstream, it doesn't necessarily make sense to do this. You might if it's what you're familiar with, but if you're more familiar with MongoDB or Elasticsearch or MySQL or whatever it is, just use whatever you're familiar with in those scenarios. So that would be a key area of when not to use it. Yes, about JSON-LD in particular, JSON is obviously one of the least efficient serialization formats anyone could ever conceive of. So a lot of people who deal with JSON don't like JSON for that reason. But of course, the counter side of that is it's ubiquitous. It's just everywhere. So if you want compact serializations, then there's other ways of getting that in much more compact formats. Now, JSON-LD is just one of many serialization types of RDF. So if you're still committed to RDF, there's Turtle, which those files end in .ttl. Turtle stands for, I don't know what the full acronym is, but terse is what the T is, meaning it's a very, very compact way of serializing and representing RDF data. So there's many formats of representing it where, if you're looking to have things in a very compact format, you might want to look at over using JSON as the main mechanism. JSON's really almost more for humans than it is for machines.
And As you continue to invest in this space and explore its capabilities and challenges, what are some of the future directions that you would like to see for overall adoption or integration with these linked data concepts in the data ecosystem, and areas where there's opportunity to bring these ideas more seamlessly to a broader audience?
It just opens up a lot of new capability. And so I'm optimistic about some of those new capabilities. We've talked about a few of them here. This idea of actually owning data, having complete control over who uses it and how they use it. Ideas around programmable data, being able to embed sophisticated security or logic directly into the data tier, I think is immensely powerful. And it's something we spend a lot of time on. The cryptography around this space, some of it is, still relatively early, but zero knowledge proofs. This idea of proving things that data says without ever disclosing the data itself is, I think, just going to open up a lot of really neat possibilities. So those are all exciting. One of the things that we're working on now is creating a human layer on top of this sort of global linked network that works a lot like GitHub, where every change is recorded and cryptographically verifiable. You have complete traceability and provenance of every piece of data. And an important thing that we have focused on in this is this concept of time travel, efficient time travel, being able to issue a query as of any moment in time and instantaneously getting a response. The reason, beyond just kind of being great for lineage and provenance sort of tracking, the reason we think this is so critical is when you are doing decentralized computing across, well, you're doing computing across decentralized data, you can't have predictable results unless you have a notion of time and can lock in time. Because if all these data sets are constantly updating, I can never reproduce the same results for the same thing. And being able to say, okay, I'm going to run this computation. It's going to involve these, 50 or 100 decentralized data sets, but I want this done as of this exact moment in time. Every one of those data sets should know how to reproduce every state of data at every moment in time instantly. It gives you completely reliable results. You can reproduce any query with the identical results at any future date, etc. So locking in time, this notion of, a fact really isn't a fact unless you embed time. So time needs to become a core component of all data management to do it. It's something we're really focused on, and I hope that capability continues to spread.
And with that question of time and evolution and mutation of data in an immutable way also brings up the question of, for what is the horizon back to which you are going to support? Like, at what point do you need to start dropping history for storage or performance reasons? And curious what your thoughts are around ways to either expand that horizon or address that need without necessarily destroying the ability to do that time travel up to a certain threshold.
Well, you want to be able to efficiently represent deltas. And as long as you can do that in a very efficient way, I see no reason to not retain complete history. But there's two parts of, managing data. One is managing sort of the log of changes. And we create, cryptographic linkages between every one of those changes. So you can prove out the entire data set. You can prove it's never been tampered with. But the other part that's used even more frequently are indexes. And indexes are just optimizations of that original log. So that's where I see you having the option, and this is what we do, of saying, I don't want to retain history in my indexes because indexes are just creating copies and copies optimized in different ways. And if the queries don't need to leverage that history, then there's no need to do it. And that's where most of the space in a database comes from. It comes from all the indexes. So I think you can do it forever. I mean, you can get a 2 terabyte hard drive now for like $20. It's just an immense amount of data. Or not $20, $100, $120 is what I meant to say. It's just an immense amount of data that you can actually store for virtually nothing. There's no reason to not have that provable history there. And if you actually look at most database patterns, updates don't happen a lot. We create a lot of new data, new records, new rows, if you will, but actually changes to existing rows are not as frequently. Now, there's certain workloads where that's not the case, but probably 98% of all data has more addition of data than they do churn of existing data. So it ends up not being a lot. It's super cheap to store. You can have completely provable data if you do have that storage. get rid of it in the indexes if you're concerned about disk space.
Are there any other aspects of this space of linked data products, JSON-LD, the semantic and ontological aspects of data attributes and data structures that we didn't discuss yet that you'd like to cover before we close out the show?
Well, I feel like we could, at least I could talk about this for a long time. We've hit so many things. I'm pretty satisfied with the ground we've covered.
Yeah, definitely lots of opportunities for more deep dives on a number of different areas. But yeah, for today, we'll leave it as is. And so for anybody who wants to get in touch with you and follow along with the work that you and your team are doing, I'll have you add your preferred contact information to the show notes. And as the final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
Yeah, I think it's helping people identify if they're starting from scratch an ontology or a vocabulary that might already exist, for their specific needs. Takes a lot of time and usually a lot of iterations to develop a really good vocabulary, and to be able to leverage other people who have thought through all those edge cases is great. And I don't think we have a lot of good tools to be able to find that. And as I said, you can just create your own and kind of do some mappings later. But ideally, if you can find something that fits your specific use case kind of upfront, that would be ideal. And that's something that I hope we can do more of, and I hope we see more of out in the industry to help people get going in this.
Absolutely. Well, thank you very much for taking the time today to join me and share your thoughts and experiences around these concepts of linked data, building products around them, and some of the ways to represent that information in a way that is usable and understandable to all of the different components that need to interact with it. So definitely a very interesting and rich space to explore. So I appreciate you taking the time today, and hope you enjoy the rest of your day.
Thanks, Tobias. It was a pleasure being here.